Is it time? Would you understand what it means to everyone? Would you understand what it means for you? Would you understand? It is time. Every few years, a technology quietly changes an industry. At first, almost nobody knows how far it will go or what it will eventually become. Long before it becomes mainstream, some fortunate researchers, engineers, entrepreneurs, and companies begin working on it. They enter when the technology is still evolving, when the answers are uncertain, and when most of the world is still watching from a distance. Years pass. Some of those technologies survive. Some become industry standards. And those early contributors become the pioneers of an industry that barely existed when they started. Today, without a doubt, we may be witnessing another such moment. But this time, it is different. The opportunity may not be in the technology itself. It may be in how future engineers are educated. India wants semiconductor engineers. Universities want industry-ready graduates. Students want employable skills. The challenge is not intention. The challenge is economics. And that raises a question rarely discussed outside engineering education. Why is semiconductor education fundamentally different from software education? Software and electronics education live in two very different worlds. For many software skills, a computer, a free compiler, and a free IDE are enough to begin serious hands-on work. Electronics adds another layer. FPGA boards, embedded kits, oscilloscopes, power supplies, measurement equipment, specialized laboratories, and licensed EDA tools all add cost and time. And unlike software, learning a language alone does not make someone ready to design electronic systems. Practical engineering experience becomes unavoidable. So the question is not whether practical training is required. The question is, can we reduce this cost without reducing engineering quality? For years, one possibility remained tempting. Open-source EDA existed. AI existed. Commercial RTL methodology existed. Individually, none of these was new. The dream was to bring them together, to let students experience a commercial-style RTL workflow without requiring the complete commercial tool infrastructure. But there was a problem. There wasn't enough internationally accepted evidence that this combination could fundamentally change. A global announcement suddenly pushed this question far beyond the classroom. A chip design exercise reported completion in just 48 hours, using AI and open-source design infrastructure. Markets reacted. Researchers reacted. EDA companies became part of the discussion. Some saw a major change. Others questioned whether a demonstration could represent production-quality semiconductor engineering. Behind all that debate, one engineering question became difficult to ignore. Can open-source EDA produce industry-reliable output? But perhaps that was not the only question worth asking. Everyone debated, can open-source tools replace commercial EDA? For semiconductor production, that demands evidence across verification, timing, physical implementation, sign-off, and ultimately, silicon. But education presents a different requirement. Even if open-source tools never replace commercial tools, they can still expose students to RTL, simulation, synthesis, constraints, reports, and the dependency between these engineering stages. And that creates a very different. Questions become useful only when they can be tested. So the workflow began producing actual engineering artifacts, initial RTL, simulation results, synthesis results, reports, and an AI-assisted workflow. The RTL had to compile, the test bench had to verify functionality, synthesis had to map the design into a technology library, reports had to provide measurable engineering results. Something interesting started appearing. Not proof, not conclusions. Evidence. Small, but growing. And that changes the nature of the problem. The challenge is no longer only technology. The challenge is evidence. One successful design cannot establish a new educational methodology. Different circuits, constraints, verification requirements, and implementation conditions must produce reproducible results. The evidence must survive engineering scrutiny, not just produce an impressive demonstration. Can enough engineering evidence be generated before this opportunity is dismissed? Before universities can evaluate it? Before students move on? Before the window closes? Maybe this idea succeeds. Maybe it fails. Nobody knows. History has shown one thing repeatedly. The biggest technological shifts are rarely obvious while they are happening. That is exactly why this technical session has been organized. Not to convince you, not to promote a technology, but to examine the engineering evidence together, to separate demonstrations from reproducible engineering, possibilities from conclusions, and questions from what can actually be measured, and perhaps become part of writing the next chapter. Is it time? That is not a question this story can answer today. The evidence is still emerging, the engineering questions are still open, and the opportunity is still being evaluated. But opportunities built around new technologies rarely wait until every question has been answered. So perhaps the better question is, if not now, then when?